I'm going to talk about AI and what it means in a few different ways. Everyone thinks they know what AI is, and especially this year. And so I'm going to talk a little bit about what it means in the context of CABBI and how that differs from the public perception of it. One important thing to bear in mind is, as far as the government is concerned, the legal definition of AI is very broad. AI is basically any computer making a decision on its own. So machine learning is a subset of AI, deep learning is a subset of machine learning, and large language models are a subset of these subsets. So I'm going to talk a little bit about those different things and what we refer to as AI colloquially in 2025. But there's an awful lot of things that are going on within CABBI that are artificial intelligence by the legal definition of it. In fact, we use it all the time, every day, in molecular biology and many of the environmental areas. But standard molecular biology, genomics, areas like this, we use these very narrow methods for machine learning, right? So we take data that is very well defined in terms of, we take data that's very well defined in terms of the input. It might be a DNA sequence. We learn tricks from it, and then we can predict, say, where a transcript will start or something about a protein that's encoded. So we're using AI as an educated guess in this case for a very narrow question. And then the alternative is, when you read about AI, people are talking about the coming AI apocalypse and things like that. If I ask ChatGPT what AI is, ChatGPT says it's ChatGPT, right? And so the large language models like ChatGPT are what people are colloquially referring to as AI. And I think we have to bear that in mind when we say we're doing AI, because doing these very narrow, rather scientifically precise, maybe a little bit boring things and calling them AI may not excite people as much. If I ask GPT to give me a picture of what AI looks like in 2025, it comes out with this giant robot and a city on fire. And, you know, that's what a lot of people are thinking about. On the other hand, Canva has this lovely, friendly robot helping children learn math. So, you know, there's a lot of different perspectives on this, and you hear a lot of it in the media. But this very narrow idea of what AI is, basically the simplest form of AI is regression. This is a machine learning to do something on the basis of data. We put the input data in, and a computer, based on that input data, if we think it's a straight line relationship, it can develop an error model based on the sum of squared error. It can minimize that error model. It can form a straight line that defines the relationship between those points, and it can then predict a future point with some degree of accuracy, and it can put a probability on how likely that line is to be correct. So a computer can learn a mathematical model from data without help from a human, and this has been possible for a long time. So regression is maybe the simplest example of this. If you take regression and you just add more terms, you can turn a regression model in 2 dimensions into a model in 3, 4, 5, 6, 7 dimensions. So regression alone can be rather powerful because you can have a 3-dimensional, 4-dimensional model. If you then modify the underlying math so it doesn't require a straight line relationship, then you can start to map surfaces in 3 dimensions. And these kinds of models that can map 3-dimensional surfaces are the ones that are very widely used in all kinds of biology at the moment, and have been around since the 70s or the 80s. And so this is AI by the legal definition. You know, we map these surfaces, we use them to predict things, and that's been around for a long time. But it's not super intelligent. It's just a way of automatically generating an approximate model for a series of complex observations. There's a few things that have happened more recently that have really revolutionized this. The idea has been around for a while that instead of just having this one mathematical model, you can have a bunch of little programs that interact, that each run different mathematical models, and those models can form something that computer people call a neural network. It doesn't resemble a biological neural network very much, but that name is stuck. So when you combine multiple different models that are measuring the distance between data points and making probabilistic predictions from them, you can enhance the ability of that system to learn patterns in the data. If you then, as has become more recently possible with more powerful computers, arrange those into multiple layers that learn from each other, we can start to do very accurate predictions of object recognition from video, for example. Andrew's group have got several examples of this. Caillou does this a lot, where you can get data from images or video, recognize things, measure them automatically, and that greatly increases the throughput you can do from various kinds of video or photography sensing. So the typical application of this, I'm going to borrow this slide from Andrew, you can take an image of a leaf, you can use a deep learning model to find where the stomata are, count the stomata, look at the patterns of the stomata, and this is something that CABBI is doing a lot through all of our different research areas. But I talked about large language models and how that is what people are talking about AI, and now this is the AI people are scared of. This is the AI that's going to take over the world and become giant robots in front of burning cities, right? So what are actually large language models doing? Well, and no, actually it's just basically the same regression tricks all over again. So what you've got is these very large matrices. You have every word in the vocabulary, usually about 50,000 words, and you measure the contingent probability of finding that word in adjacency with every other word in the vocabulary. And you end up with a graph like this one at the bottom left, which is a graph of embeddings, the probability of finding two words together in syntax. And so what this matrix-based word probability model does is you give it a word, and it'll chuck back a whole lot of other words that are very likely to occur in context with that word based on an enormous amount of human-written text that that model has ingested that's come from the internet or scientific literature or something like that. And so it kind of doesn't always make sense. So these early chatbots didn't always make coherent grammatical sentences that made sense to humans. The breakthrough that happened recently was the GPT, the general purpose transformer, which is adding a neural net on top of these probabilistic word models. And the neural net is then capable of constructing syntactically correct sentences that actually make sense to humans, based again on the syntax and grammar that it has learned from massive data sets out in the public domain. So that general purpose transformer plus these models of word probability is all that's going on. So if you ask a large language model, what is the sixth element on the periodic table, it will give you the right answer, even though it does not know what an atom is. It does not know what the periodic table is or how it's organized. All it's doing is it knows that sixth element and periodic table, you see that together, and it's going to pull back carbon because that is the word that occurs most commonly in that context. So it looks like it knows stuff and understands stuff, but actually all it is doing is giving you the most likely words in the context that that was delivered in the training data. So they're very, very good at writing text that looks nice, looks like a journal article, looks like a newspaper article. You can say in the style of Edgar Allan Poe, and it will write in the style of Edgar Allan Poe, because once you see that in context, it knows what Edgar Allan Poe's writing is and how that alters the contingent probabilities of the words. What it's not good at is getting scientifically accurate things right based on its background data set. And I'll talk about this a little bit in my next talk. There are some ways to adjust that, but in general, it's really bad at getting numbers, math, logic, scientific source material, getting those facts actually correct. I'm going to give you a simple example of this. So this is Hans Muller, who wrote the Kropser algorithm in my group. And he's now in Brazil, but he was instrumental in doing starting a lot of the stuff in my lab. He asked one of the large language models about himself. And it actually found a lot of data about Hans because his biography's on the CABBI website and things like that. And it gets most of it right. But actually, he it gets a few things wrong because it's only looking at word probability. So the University of Campinas is not in Sao Paulo. He questions the fact that he's published several papers in top academic journals. He thought that was a bit of an exaggeration. And it says he enjoys playing soccer, right? And actually, he hates soccer. But because he's Brazilian, the probability of him liking soccer is very, very high. So it comes back and says that he likes soccer because that's the highest probability answer in the word embedding model, even though it's wrong. And so in a scientific context where we're trying to do novel things, these models are quite dangerous and we have to use them with a lot of care. And they're really not as frighteningly intelligent as you might think. So just to give a few examples of projects that use AI across CABBI, I'm not going to go into details of all these. Many of them will be dealt with in other talks, but AI at many levels, including large language models in several groups, but certainly these broader defined AI things are essential to almost everything we do. We not only use them, we develop new models, and that's only growing as the center expands and becomes more computationally driven. Okay.